Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. This is the guided notes number 4 in the series on section 1.4, Complex Zeros of Polynomials. Let's first recall the definition of a complex number. Formally, we say that z is a complex number if it can be written in the following form: a plus bi, where a and b are real numbers, that is to say just one of our friends from the number line, and I can be defined as the principal square root of -1. You can treat I as a variable in the same way that you would treat an x, for example, when it comes to things like grouping like terms. It, however, has this additional property that if you were to square it, you would get -1, which will simplify powers of I. Let's then address this first problem on how to simplify the square root of -32. Any negative number can be seen as the positive number times -1, and like other exponents, square roots, which are 1/2 powers, distribute around products and quotients. Hence, in light of the previous definition of I, we have that we can pull out this negative sign as an I and deal with the square root of 32, the positive number, separately. Now, 32 is equal to 16 times 2, where 16 is in fact a square. And that means that the square root of 32 is equal to the square root of 16 times the square root of 2. Hence, we can rewrite this as 4 times the square root of 2 and simplify the numbers inside the radical a bit. This means that our original problem could be rewritten as 4 radical 2 times I. You'll sometimes see this as 4I radical 2 because multiplication is commutative. We can write that however we like. But it's a bit more common to see the i's written at the end of the expression, because this more closely fits the form 0 plus 4 radical 2i, where now 0 and 4 radical 2 are my real numbers a and b respectively. So for the remainder here, I will be writing the i's at the end of the expression when I go to write an answer. Let's now do a small review of complex arithmetic. These parentheses are purely organizational, but we're just adding two things together, and as such, we could drop these, and now using like terms, we could group these additions together, and the distributive property shows us how we can just, like if this was an x, just take the difference of these two coefficients to give us -1 plus 3i. Now, I wanted to write this with too much work shown because it lets you see the more general form of addition of two complex numbers. If I have two complex numbers, a plus bi, and I add that to c plus di, really all I need to do is add up the coefficients of the like terms for the real and imaginary parts, respectively. We call these the imaginary parts of the complex numbers, and we call these the real parts of the complex numbers. With problem 3, this set of parentheses is organizational only, but these are kind of essential parentheses. We need to see that we are subtracting both of these terms. And as such, this could be rewritten as -7 plus 4i minus 7 plus 4i. We need to distribute this negative against both of these signs. And again, grouping like terms as before, we now get this expression. We should note that we have a very similar formula to that of addition, where now we are simply taking the difference of the real parts and the difference of the imaginary parts, respectively. In order to carry out complex multiplication, what we're going to want to do is FOIL. We're going to want to take the first terms, we're going to want to look at the last terms, we're going to want to look at the outer and the inner terms, respectively. And one of the reasons that I'm going to color code them this way is because when we take our last terms, we're actually going to see that the I squareds will simply change the sign of the product and give us a real number again. So let's take a look at each one of these. We have -5 times -9, that's +45. And now let's do the last one. We have -i times 5i, that's -5i squared. Likewise here, for my inner and outer, I have -i times -9, that's +9i. I've got -5 times +5i, that's -25i. But my I squared term here we've discussed is -1, almost by definition. And so this really just turns into a +5. That makes the real part of this expression 50, and the imaginary part -24. So we have 50 minus 24i. There is a formula that could be employed here. By foiling these and collecting like terms, we would arrive at, once we took into account that I squared was minus 1. And while this equation is true, it's starting to get close to less than useful because of how many pieces are in it. That we have a difference of the first and last terms, and then we have the sum of the outer and inner terms. But I think it's better to remember that we FOIL when we multiply complex numbers and simply follow the rules that are associated with like terms and I squared being minus 1, and then see where that takes us, rather than try to memorize some formula. And that is especially true when we start to look at problem number 5, complex division. Now, complex division is going to take on a very different feel from the last of these because it, unlike the others, requires a certain trick. To justify this trick, I would like to discuss the complex conjugate briefly. So the complex conjugate of a number z, which let's say was equal to a plus bi, the complex conjugate of this number would be written z bar with a line over it. And that would be a minus bi. Notice that we kept the sign of a, the real part does not change, and the imaginary part changes sign. A very important property of the complex numbers has to do with difference of squares. Let's recall that if I had a plus b times a minus b, what we would wind up with is a squared minus b squared, because the middle terms would cancel. Now, something very similar is going to happen when we multiply a number by its conjugate. If I take a complex number, z, and I multiply it by its conjugate, z bar, what I wind up with is the following. As in difference of squares, the middle terms cancel, and we wind up with a squared minus b squared I squared. However, the I squared, of course, goes to minus 1, and so this becomes a squared plus b squared. So the sum of squares really did have a factoring form. It just actually requires us to utilize complex numbers in order to do so. An additional tidbit worth noting is we graph complex numbers by plotting the 2 points A and B as the real and imaginary parts on the x and y axis respectively. Then my complex number is this here. So we consider this to be sort of the I number line, the imaginary number line, and this would be a plus bi as a dot. Well, that dot has a distance from 0. Just like other absolute values, we could consider this length to be its absolute value. And looking at this, we actually have a right triangle pretty clearly visible. So we could say, right, using the quadratic equation, that the absolute value or the magnitude of z was equal to a squared plus b squared. So we have this rather interesting property that multiplying a complex number times its conjugate gives me its absolute value squared. But the main point here is that that number is a real number. In fact, it's a real positive number. And the fact that it is real when we multiply a number by its conjugate is what is going to allow us to use the complex conjugate to do complex division. Because as it stands right here, I cannot simplify this any further. The denominator has a sum in it, and that's not going to cancel easily. So what we're going to need to do is rewrite the denominator in such a way that lets it be reduced to a single number. And then that can distribute, and that can cancel easily. To do complex division, we take this number in the denominator, and we multiply the conjugate of that on the top and bottom. So not changing the real part, but changing the sign of the imaginary part, we get a conjugate, and multiplying by something divided by itself will not change the value of the original thing, because this is effectively 1. It does, however, change its form in a very important way. If we look at multiplying the two denominators together, we see they are a number and its conjugate. And so we multiply the minus 1s, we get plus 1. We multiply 6 and minus 6 to get negative 36, but that's negative 36i squared, in fact. And so this would turn into a minus 1, and this minus 36 is in fact a plus 36. Now in the numerator, things are a bit more general. We have to still FOIL in order to get the new value of the numerator. This is going to be minus 1 times 29, that's minus 29. We have minus 6 times positive 11, that's negative 66i. but the I times I will give me I squared, and so this is going to turn into a plus 66. And my inner and outer terms are going to be minus 11I and negative 6 times 29. Well, 30 times 6 would be 180, and minus 6 would be 174. So this is going to be minus 174i. And let's now simplify, right? We have some arithmetic we can do. This is going to be 37. This is going to be positive 37 itself, and negative 185i. Now, we could, of course, distribute the 37 against both of these. 37 divided by 37 is 1. And I wonder if 185 divided by 37 is some whole number, or if this will maybe reduce. But just thinking about it for a moment, there's a 5 here and a 7. I wonder what would happen if I multiplied by 5, right? We'd get 35 would be the 7, but then 5 times this would be 150, and summing them would be 185. So either with a calculator or a little mental math, we can figure out that's going to be 5. And this is, of course, because now that this is a single number, I'm allowed to divide it into each term. I distribute 1 over 37, respectively, into each of these terms, and I wind up with a nice simplification. And following that procedure in its generality, we could produce a formula, but even more so than the multiplication formula, I don't think this is as useful. I think that it is better, in fact, to simply think about what is going on in this particular step. We are multiplying by the conjugate of the denominator. And after that, we're literally just following our nose about where the multiplication of these top and bottom complex numbers will lead us. We eventually get a real number in the denominator, which lets us finally write this in term looking like a complex number. This is a real number, this is a real number times I, and so we have the correct form of a complex number. So just remember this trick. What do you do to divide a complex number? You multiply by the conjugate of the denominator on the top and bottom. Here we have a question about conjugates. What is this conjugate? We simply change the sign of the imaginary part. Now, an equally good question is what happens if it is a purely complex number, or I should say a purely imaginary number? Well, we just change its sign because its real number part is 0. On the other hand, what if I have a real number and I conjugate it? Nothing happens because we keep the sign of the real part of the complex number and we only change the sign of the imaginary part of the complex number. So if there is a pure imaginary number, it changes its sign completely. And if there's a real complex number, because real numbers are also complex numbers, real numbers are complex numbers of the form a plus 0i, then that real number will not change at all. Complex conjugation does not change real numbers. Problem 7 is a hasty digestion of the fundamental theorem of algebra. The fundamental theorem of algebra tells us that if the degree of a polynomial is n, then p of x has n zeros, counting multiplicities. A multiplicity is the exponent of a certain factor. So, for example, if I had a polynomial such as this, then we would say it has a 0 at minus 1 with multiplicity 1. No exponent here, it's to the power of 1. It has a 0 at positive 2 with multiplicity 2, and it has a 0 at minus 10 with multiplicity 3. And if you just imagine expanding these polynomials, we would get a first power, a second power, a third power, and multiplying those first terms together to get the largest exponent, we would wind up with something that looked like x to the 6th plus smaller, lower order, lower exponent terms. And so the degree of our p of x would just be 6, and it has 6 zeros. It has 3 distinct zeros, but it has 6 zeros when we count with multiplicity, when we sum the multiplicities of each 0. And so with that in mind, this has 4 zeros, this has 3 zeros, and this has 5 zeros, respectively, because the degrees are 4, 3, and 5, respectively. The following problem 8 says, use any means necessary to solve 9x squared plus 6x plus 50 is equal to 0. Well, it's a quadratic, right? So we could use the quadratic equation. We might try to factor, but let's consider sort of a combination approach, right? If I have a, b, and c here, I could pretty quickly figure out what is b squared minus 4ac. And the answer would be 36 minus 4 times 9 times 50. And we can definitely see that that is going to be a negative number, right? We have this very large number that we're going to subtract from 36. In fact, if you can see that this is going to be 36 itself right here times 50, it probably doesn't surprise you too much that this is minus 49 times 36. But let's come back to that. Perhaps you didn't see that. Perhaps you just saw that we needed to do some subtraction here and that this would be 36 minus, let's see, 4 times 50 is 200, times 9 would be 1800. And this would give us something like 1764. Negative, of course. Now, I encourage doing this part first because it tells us whether or not it would factor. This isn't going to factor over the reals. It would factor over the complex numbers, but not over the reals because this is a negative. And so when we look at the square root of this thing in the quadratic equation, it's going to give us a complex number. So let's actually just carry out the rest of the quadratic equation. We know that's going to be x equals negative b plus and minus square root of b squared minus 4ac over 2a. And we haven't really lost much time here because we already did the discriminant. This is negative 6 plus and minus the square root of negative 1764 over 18. Now, if you did notice that this was 36 times 50 and therefore we got negative 49 36 times 36 here, you're probably not too disconcerted that this is a square. But you could also try square rooting it, and what you would find is that this is 7 times 6, or 42 squared. And so what we wind up with is minus 6 plus and minus 42i over 18. Now, distributing the 18 and reducing, we have two complex numbers. We have minus 1/3 plus, dividing both of these by 6, we have 7/3 I, and we also have its conjugate, minus 1/3 from this minus 7/3 I. And this is in general part of a fact about real coefficiented polynomials, which is that if a complex number is a solution, then its conjugate must always be a solution. I will sketch a proof of why that is the case. In order to prove that, you first show that if you have two complex numbers a times b, then if I conjugate them, that is the conjugate of a times the conjugate of b. From this, plus a technique of proof called induction, we can show that if I have a complex number to some power and I conjugate it, then what I will wind up with is that complex conjugate to some power. And hence, if I take a polynomial, let's say p of x, where all of my coefficients are real values, well, recall that a real number, if I complex conjugate it, is just itself. And so if I know that a certain value plugged in here, let's say the value z, will give me a 0, well, taking the complex conjugate of both sides, I would simply get 0. And on this side, what I would wind up with is the complex conjugate of the entire polynomial, which reminds me, we don't just need that products distribute the complex conjugate. We also need the more obvious fact, which is that sums distribute the complex conjugate. Let's just make a note of that. Then we could see that the polynomial would just distribute the entire complex conjugate. All of its coefficients are real, so that's really just saying that z bar is itself a root of p of x. So there we have it. If we know that p of z was equal to 0, then we also know that p of z bar is equal to 0 if my coefficients of the polynomial were all real. And that's going to be the primary focus of this particular section of algebra. We're going to be looking at real valued polynomials still, and we must know at least this fact. If this proof is a little bit above your pay grade, don't worry about it. I actually used, I alluded to induction, which is something we might be able to brush upon later in the course, but you don't need to follow the proof line by line. If you're interested, that's fantastic. Dive into it, ask me questions about it if you want. But the main thing you need to know is that if I have a 0 of this form for a complex zero of this form, right, a plus bi, then a minus bi is also going to be a zero if we're talking about a polynomial with real number coefficients, which this one is. So, for example, problem 10 says, if this is a zero, what other zero does it have? Well, certainly then f of minus 1 plus 5i will also be zero. We must know that the complex conjugate is another zero because that's actually going to let us reduce a polynomial or factor this polynomial by a degree 2 polynomial rather than just a degree 1 polynomial if I'm given a complex root. It's better to be given a complex root. We can reduce that polynomial even more than if we were given a real root, because we know this additional fact about complex conjugates. Oh, right, problem number 9 is, of course, a straightforward application of the quadratic equation. We can't completely simplify the radical this time because 108 is 36 times 3. We can only pull out a 6. But once we do that, we can simplify with a 2 and get these two complex roots, -5 plus 3 radical 3i and -5 minus 3 radical 3i. So now let's push a little further into the consequences of that fact that a complex number will have its conjugate as a root if it itself is a root, to see if we can find a degree polynomial with real coefficients having zeros 4 and 4i. So if 4i is a zero, then minus 4i is also a zero. If a number is a root, its conjugate is also a root. And they want us to write it in the expanded and factored form. Let's start with the factored form. That will be easier. Our polynomial f of x is going to have the following factors. We'll have minus 4 to give me this root. We'll have minus 4i to give me this root. And we'll have minus 4i to give me this root. Technically, there's going to be a little c up front because timesing by a constant does not affect my zeros if this is a non-zero constant. And we're going to need that if this coefficient needs to be something other than 1, because when I FOIL all these things together, we're going to wind up with x cubed, and with all of these 1's in place, it will still just be a coefficient of 1. So oftentimes there will be an extra step if we need this to be something other than 1. I'll include the c in this case just to kind of showcase what that extra step should look like. Now, this isn't quite a polynomial in terms of reals yet. This is a polynomial in terms of complex numbers. So let's first of all rewrite this as plus 4i. That part is obvious. And let's expand this to get a factored form of a real polynomial. So x is x squared. Your last terms multiply to give me minus 16i squared, so that's just plus 16. And your middle terms cancel because this looks like difference of squares, and we're done. Now this is factored and is a real polynomial. If we wanted to expand it, we could go a little further and FOIL this, which would give me c times x cubed minus 4x squared plus 16x minus 64. And again, if this were a more complicated problem, I would be looking at this term here and saying I need it to be 1 after distributing the c, but we can see that that's going to imply that c is equal to 1, which we really could have imagined just from the very beginning. So at the risk of being a little confusing, I'll just say that c must be equal to 1 at this point, and we could write x cubed minus 4x squared plus 16x minus 64 itself without that little modifier up front. This is also, this inclusion of a constant multiple here is also what you would do if they told you something like, p of 0 is equal to minus 64, and you wanted to find the polynomial that passed through exactly that point. Well, you include this constant multiple of c and then figure out what exact value of c would make that true. Of course, for the example that I just gave, that would also mean c was equal to 1. So, moving on. Here they ask us to find all the zeros given a certain factor. So we sort of covered this procedure in the real polynomials video. What we're going to want to do is divide out this term. We're going to divide this from the polynomial either with long division, or in this case, because this is a simple linear term, we could use synthetic division too. So let's do synthetic division. It's a bit faster. We encode our coefficients. This has a root of 5, and we drop the first one down, multiply these out, and continue. And we better get a remainder of 0 here. They guaranteed us that this was a factor, so I certainly hope that we'll wind up with a remainder of 0 when I divide by a factor. And this gives us the fact that this will be equal to x minus 5 times 4x squared plus 12x plus 11. And now that we've reduced the polynomial sufficiently, now that this is only a second-degree polynomial, we can just use the quadratic equation to complete the rest of the 0 finding. We have a equal to 4, b equal to 12, c equal to 11, and this is going to give us zeros of, like, let's say this was equal to 0. What would x be? Well, it could either be 5, or it could zero this polynomial out, which happens when x is equal to this expression. Doing a little bit more of this arithmetic, we find the following, which simplifies to once we simplify those fractions. So here we have the remaining zeros. How do we know that's all of them? Well, because we have 5. So if this is 0, x could be equal to 5, or x could be equal to these two. And the fundamental theorem of algebra tells us that it's only going to have at most 3 zeros if each 0 has multiplicity 1. To address problem 13, what we want to do is first note that if a complex root has been given, we also know that its conjugate must also be a root. Now, roots, aka zeros, correspond to factors. 4 plus 3i is a root, means x minus 4 plus 3i must be a factor. If 4 minus 3i is a root, then x minus 4 plus 3i must be a factor. Now, if I FOIL this out, I get x squared. My inner terms give me minus 4 plus 3ix. My outer terms give me minus 4 minus 3ix. And we want to multiply these last terms together. A negative times a negative is a positive, and 4 plus 3i times 4 minus 3i will be our final term here. Let's notice some simplifications that go on. First of all, the 3i minus and 3i minus minus is plus are going to cancel with each other. So these middle terms aren't going to have an imaginary part. On the other hand, minus 4x and minus 4x are going to reinforce. And we're going to need to FOIL the last term. FOILing will have the first two, the outer product. We're also going to want to FOIL this last term. The 4 times 4 and 3i times minus 3i are going to persist. We'll have minus 9i squared, which is going to be plus 9. So we'll have 16 plus 9 here. But these middle ones are going to go away because we're multiplying a number by its conjugate. So we have 4 times negative 3i, that's minus 12i, and positive 12i. They'll cancel. So that leaves us with x squared minus the 8x from the reinforcing middle terms here. And then this 9 plus 16 is going to give me 25. And now multiplying our last terms together, this number times its conjugate will give me cancellation of the middle terms, and we'll get 4 times 4, that's 16, 3 times minus 3, that's minus 9, but I squared is negative 1, so that makes it plus 9. 16 plus 9 is 25. Continuing on, we would like to divide our f of x by this new irreducible quadratic factor. So we write f of x in the quotient, we divide by this new factor, and we should get remainder 0 if it's truly a factor. 2x times x squared will give me 2x cubed. And continuing to multiply 2x by each term times minus 8x gives me minus 16x, times 25 gives me 50. Ah yes, this is of course x squared. Let's not forget that. So multiplying by 2x against minus 8x, we get minus 16x squared. Multiplying by 25, we get 50x. And taking this difference, we're going to wind up with, first of all, a single x squared, and then minus 8x. Now dropping down the 25, we see that this is in fact my divisor, and that's great because that just means we need to multiply the divisor by 1, and then we know it's going to have a 0 remainder, which we expected. This quotient is our new linear factor, and now we can actually write both the factored form and the roots. We now have that f is 2x plus 1 times this irreducible quadratic factor, and that means that zeros are going to be 4 plus 3i is given, 4 minus 3i its conjugate, and negative 1/2 that we get from setting this equal to 0 and solving. That's going to do it for this particular section and this particular worksheet. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.